So comment I have before the start is we're sleepy. But I would say 9:30 is not very early, but I think it's still early in some sense if you sleep late. As the people in Hong Kong, people tend to sleep pretty late. So 9:30 is but I have had 9 a.m. 9:30 classes yesterday as well. So every day I have morning class, but that's why I have a coffee with me. So in case you need, feel free to get a coffee during the break. That's pretty useful. So as some of you I confirm is the job period ends this Saturday, right? Or Saturday, right? So I will be taking attendance next class onward. Okay. Either probably through the reply. So ask question and you write down things, and then the record know who is replying. Okay. Now let's get back to the business. The goal of today is to introduce you the modern version of probability. Okay, that is without the idea of engineering or empirical idea, right? Because we studied last time, probability is based on a long-run frequency, right? It's still based on things we can do, we can repeat. But what about things we can't repeat, right? Technically can't repeat, right? Just like typhoon signals, right? Actually, every typhoon is unique. You can't really assign probability in the classical sense. But still, we can say probability in a fair, reasonable way, because using physics, using engineering, using some science knowledge, we can say, although not entirely the same each typhoon, but there's some fairly similar thing if you look at the scientific feature of the climate, right? The environment, the natural environment. So we have some trust that our knowledge about science can help us to know the direction of the typhoon, right? So that something can't repeat can still say something. So we need to give you a mathematical model or to understand how we can define probability that without defining through a random experiment. Okay, it's through a math. The minimum assumption we do is to construct based on math. Okay, unfortunately, we have to use math because we want things without real world, without experiment. We have to, based on our calculation or quantify the uncertainty, which is the probability meaning, right? Which is through what we call some axiom, is invented by Russian mathematician in the hundreds ago, okay, 1920 something. Okay, but then that builds the foundation of the probability we use for everything. Okay, all the finance calculation, right? Because suppose I want to see the stock market, the stock today is going to go up and down. Okay, that would be the thing. Okay, now I have the reply in case you still want to say something. You can feel free to say something. Just I want to know if you have anything to say, but otherwise, I guess there's no need. You can tell me what you think during the break as well. But I just end the pre-class you reply. Okay. Now let me review quickly what we have done last time. That is a classical probability definition, which rely on something you can repeat. The random experiment, because they started from a gamble. If you know the history, is starting from those mathematicians during the 1700, Fermat, Brignoni, those math people who are nobles and have a lot of time to waste, and then they do a lot of gambling. And because then the gambling, they figure out what is the fair gamble. In order to calculate fair gamble, you have to quantify uncertainty, right? So make sure that the winning odds are same as the probability that those things appears. Okay. And the simplest thing you can see is the toss a coin and roll a die. right? There's a random variable. And for gamble, of course, you know what's going on there, right? What may be the outcome, so they can bet, right? And that can be repeated, okay? And outcome are the outcome, the possibility of random experiment, and event are groups of outcomes. And we will use the set notation curly bracket to write down all the outcomes. And also the sample space, right? That's how we write, also using a set notation there, right? And the probability as a long-run frequency. So in the classical sense is you can only assign probability that things can be repeated. And those people who still believe in this one firmly are called frequency list. That's why this is called the frequency list probability, because they believe the probability should be only defined by long frequency. Okay, so give me example. What is probability was not in this wheel? So, for example, in a classical drama, right? A man have a romance over a woman, right? And then he sent a gift, maybe chocolate or flower, okay, to her, and he doesn't know whether the girl like him or not, right? Whether she would throw away his gift, the chocolate or flower in the rubbish bin, right? So if for this guy, okay, in the classical sense, there's no probability that whether she throw it away or not, because it's either she throw away, she does not, right? It's a yes no question. You just don't know. There's no probability, okay, according to this wheel. But if later we talk about the Bayesian wheel, it's possible to say it, because the Bayesian wheel is invented by Bayes. It's just like, although it's not 0 and 1, but we can, the probability we represent our belief. What we think, we quantify what it is. Okay, it's like opinion, right? The probability can be used as opinion, although this thing can't be repeated. Okay, but the probability reflects how we think about this. Okay, it's sometimes we call subjective probability approach. I think it's start from Simons in the 50s. But that we will talk about this a little bit later. We call it, there's the most important theorem at the end of this class is called Bayes rule that associated with that. Okay. But we start with the frequency list approach. Everything can be repeated. We can do it. Okay. But as I said, typhoons, science prediction, this doesn't fit very well. Okay. Because not every typhoon is different, right? Because the environment is so different every time. So technically you can use this. Okay. But we're still safe to say this, the probability from science is still okay, right? But anyway, remember this as example, show you that how you can calculate probability, okay, by experiment. Okay, you roll a die 6 million times. If the die is fair, each outcome appear 1 million times, right? And then basically probability, we're just counting the ratios. So I'm not going to repeat this one. Okay, and if you do it the die twice, then do note that this example remind you that the order would matter. Okay, if that is matter for your application, right? But in the case that you are a business person, say the die number is the amount they spend in your restaurant, you not care about the revenue sequence, but rather you care about total revenue. You care about the sum, then you don't need to record the sample space as for the 6-1. Instead, you only care about the sum, which only have a value of from 2 to 12. We only have 11 outcome, right? But if you care about the order matters in your case, then sample space will be larger. So the sample space is depend on how thing you can measure, right? It's depend on your ability or technology of measurement. Okay, but of course, it also depends on what's the purpose of your application, right? Suppose you are financial market, right? You're betting on the futures or options on the stock index, right? Then you don't care about whether stock A goes up or stock B goes down, but care about the final index, right? But if you're betting your portfolio differently, right, and then you care about different thing, right? You have option on different stocks, then different thing will mean difference, right? So it really depends on application, the sample space. So you have to be a little bit more careful about this one, because depend on how things you can measure, right? So as I said in the beginning, unfortunately, we have to introduce some math concept because we want to define probability without relying on random experiment. So we have to rely on something that is the mathematical structure, is the math. The first time for you to learn it, you wonder why we need math. But if you want to study something, if you don't want to use the real world thing, we have to use some math. Okay, that is frequent in science or chemistry. So bear with me, we need some math. Okay, so first thing we need to define, which is something you know very well in logic or in English, is what we call intersection, union, or complement, and that is actually English word of the first one, intersect, is called and. The second one is called or. The third one is not. I guess you know the English, then it's intuitively what it means. Okay, because we want to have two event. Okay, and if I want to find a common element, that's called the intersect. We'll give you example more. Or is I take all the element in both of the events, and not will be I just pick up the things that is not there. Okay, don't worry, I'll give example. But this is just an English word in your mind. But if you ever learn logic or set theory for mathematics, or if you do the M2, then you have already seen it. Okay, in Hong Kong, M2 math, or you are in other place in the world, you learn advanced math in high school, it's there. But as I said, we don't have assuming anything, we start from scratch. But don't worry, it's very simple. So as I said, the intersect simply means you find all the common element there. Okay, you wonder why we need to math, but I said I promise you, once you understand the math, we can only define probability. Okay? So just you have to pick up the thing that is common to all. Okay, where is the word? Yeah, all common. So here we have sample space is 1, 2, 3, 4, 5, 6. Even number is 2, 4, and 6. Maybe 2, 4, 6. So for people who in the Zoom can see, right? E is 2, 4, 6. Odd is 1, 3, 5. Large is 4, 5, 6. So for intercept between E and L simply means you pick element that common to both. How do you do that? Look at, you can pick any set, say E or L, pick the event E. Look at 2. Is it 2 in L as well? If no, that's not. Look at 4. Is 4 also in L? Yes. If 6 also in L? Yes. Okay, then you're done. You only need to pick up one of them and try. And so O and L will be, you pick up one. Is it in L? No, that's not. Is it 5 in L? No. Is 5 in L? Yes, only left 5. So you can try yourself and see E intersect O will be an empty set. It's nothing. There's nothing in common. Okay? So the empty set will be denoted as a 0 and across it. Okay. So that's intersect. So intersect means take everything in common. That's it. That's N. Okay. So the idea is easily seen in the Venn diagram. You draw a circle, contained the E will be 2, 4, and 6. L will be 4, 5, 6, right? And the common element is the overlapping area, which is 4 and 6. So that's the E intersect L. Okay. So sometimes people call E cup L. Okay. This sometimes refer to the caps, cap symbol. the cap is the head, the cap E cap L, or you want E intercept L. And the other is union, just pick up all elements in either of the event, so of everything there. So if you have E union L or E cup L, basically you write wherever thing is there. So you just write the first one, right? You just copy to here, and you just see 4 is already there, don't worry about it. 5 is not, then put it in. 6 already there, so just you put everything there. And O and L will be, you just pick up everything there, okay? And if you can see if E union O will be just S, okay? If E union O is everything, that's basically S, okay? So I hope that is not too difficult. So basically just graphically is everything there, okay? Everything in the both circle there. Now, the last one is not, the English word not, okay? Which is not there, just outside that, right? So it's not in the event. So if you're even, okay, and we know even, if not even, that must be odd, because that means that if even, that's actually the odd. How will we do that? That's amazingly simple, because even is 2, 4, and 6, which means that you go to the sample space. You find 2, you cross out. You find 4, you cross out. You find 6, you cross out. So what is left over will be the complement. Okay? The complement simply means not. Okay? Is that okay? And if your large number, the complement will be small number, right? Because if not large, then must be small. So large is 4, 5, 6. Small is 1, 2, 3. I hope that is not something too terrible. Is that okay? Is that okay? So if you look at the diagram, here will be have E will be even numbers inside, right? Outside is 1, 3, 5, right? Because everything is there, should be. Now, I guess now we go to a little bit more challenging, okay? Because after that we can define very important concepts. Okay? Now we define an important concept. It's called mutually exclusive. What's that? Mutually exclusive means that if one is true, the other must be false. Okay? That means that they can't be both true. Okay? But do note that they can be both false. Example include the following. You are here now in the classroom 2011G, I suppose, right? Then if you're here, you can't be sleeping on your nice little bed, okay? Drinking coffee and watching YouTube or playing TikTok, right? Those are mutually exclusive, right? Either you're here or you're lying on the bed playing your phone, okay? If you lie on the bed, you cannot be here. You're here, you can lie on your bed, right? So one way or the other. But you need not be both, right? You can be go to the cafe, drinking your coffee or tea, right? Or you can be library, you can be elsewhere, right? So it just can be, you only be, if one is true, the other must be false. But it can be, both of them are false, okay? It simply forbids you to have both of them are true. So the definition is just, the interset is empty, so it can't happen to be true for the both. There's no outcome that lead to both of them is true. Okay, that is called mutual exclusive. Okay. If you law, that is the thing, right? If there is a murder happen, right? So if not in there, you can't really kill it, right? So you're gonna kill the people, right? So that is, you are doing a mutual exclusive thing. And we have another one. We have exhaustive. Exhaustive by English means that you use up everything, right? What do you mean use up? Means that there's nothing left. So use up means that you are talking all possible cases, right? And there's nothing left. Exhaust the thing. And means that if the event you all mention exhaustive means that you mention all the possibility and at least one of them is true. So the definition is exhaustive means at least one of them must be true. That means that it can't be jointly false. Okay? For example, it's like this. If you're happy and you're not happy, must be exhaustive, right? Either you're happy or you're unhappy, right? You're not happy, right? Either one or the other, right? And I think there's a famous commentary when you look at the football penalty kick. I guess there's a very famous statement by a Hong Kong commentator say, now it's penalty kick. There are two outcomes. Either the ball get in the net or they're not. Okay. So it's with tautology, right? But that is what it means, right? You mention all possibility. Right? And that's what happened, right? I don't know now these days they still have this in the TV, right? It's often there's a girl at night thinking about a boy she has romance with, and he hold a flower with a lot of petals, and he throw away the first petal that he loves me, and the second petal he doesn't, and that's what he does, right? Until the end, and he figure out what is the prediction from the flower petals, right? And what he do is exhaustive, right? Because it's either the boy loves him or the boy doesn't, right? So it's exhaustive. Okay. So basically, it means the union is the sample space. Okay. Now, these two special things, if you combine together, will give us the most useful thing, which is what we call partition. That is the most important in our definition. Okay. Because we discuss all this until now to reach this slide is to define partition. Partition is the combination of mutually exclusive and exhaustive. Remember, mutually exclusive means at least if one is true, the other is not. Okay? It cannot be jointly false. So at least one of them is true. And exhaustive means one of them must be true. Right? So that means that if the things are mutually exclusive, exhaustive means that at least one of them is true and only one of them is true. Okay? One of them is true and only one of them is true. Okay? So graphically, actually, it's very simple. It's just what you do when your birthday. Okay? Your birthday, you have a cake, you cut it, okay? Everyone at 1 pieces, right? You would take 1 pieces, right? So that is what we have. That's called the partition. So to remind you that this is the most important idea. Okay. You may ask why this one, but later you will see this is the fundamental property of probability. Okay, which essentially we will see in the axiom, saying that the probability of the sample space is actually the sum of the probability of each individual component. Okay, basically it's just sum of its part equal to sum of the whole. So that is the main probability thing. But we will do it now. So if you're okay, we are ready, then we will define probability. But before that, we give you example to demonstrate the idea again. So we have the DOTE die of number 6 with even number, odd number, prime number, and B is the big even number. Okay. And you can see O and B are mutually exclusive because the interset is empty. So if O is true, B cannot be true, right? If B is true, O cannot be true. But it's not exhaustive, right? Because when 2 happen, both of them can be false. Okay. And OPB are collective exhaustive because if you roll a dice, any number comes out and at least one of them is true, right? Can be, say, if 1 comes out, O is true, 2 comes out, P is true, 3 comes out, O and P are true, right? 4 comes out, B is true, 5 comes out, O and P are true, and 6 comes out, B is true, okay? And what is mutually exclusive exhaustive is even odd number, right? It's either even or odd, right? And only even and odd, one of them is true. Okay, cannot be both true, and at least one of them is true. Okay, so that is what they call partition. Now, if you're okay with this definition, we'll now get into serious business because we'll introduce you the 3 axioms of probability. So by these 3 axioms, 3 property that can build up probability definition without relying on the real world. So rely on our faith on these 3 axioms. So if you take them, then that's the probability. Okay. So axiom means if you learn math, geometry, that's every geometry will start with axioms, right? With the 5 axioms, right? This axiom is same that this is the thing we take. We believe that these are the assumptions that we will hold it. Okay, it's true for what we mean by probability. Okay, and probability is simply one thing. It just they give me an event, I tell you a number, right? Because that's quantify the uncertainty. And the first axiom say, give me any event, I will give you a number that must be between 0 to 1. Okay, of course, we say the larger the better, but you give me the number, the only restriction is it must be anything from 0 to 1. Okay. And did actually we did in the classical case, right? The classical case is a fraction. Fraction must be 0 to 1. Okay. Is that okay? The first axiom. Very simple. We just simply said, okay, you give me an event, I'll give you back the number. The number must be between 0 to 1. Okay. I think that is not very strong restriction. When you quantify the future, must be between 0 to 1. Okay. And you may say, okay, is it some restriction at all? Yes, it is, because even before the probability, people talk about odd ratios, which we will define soon, right? Later in today, hopefully. The odd ratio is not between 0 to 1. And the classical way to, if you do gambling betting, right, you will know odd ratio. Okay. And I think if you read now the newspaper today is the government allow betting on basketball, but betting will have an odd ratio. If you go to casino, they don't talk about probability, they talk about odd ratios. And odd ratio is a way to quantify uncertainty as well. You start from 0 to infinity, right? The infinity is the most likely, right? 0 is very unlikely. Okay. But now we have a probability, also quantify uncertainty, but we restrict to 0 to 1. Okay. This probability is a measure of uncertainty, but we restrict to 0 to 1. You can do another thing, but that is the probability did. Okay, this first axiom, nothing to remember. I think there's something trivial. Okay. The second one is also looks like trivial, but it simply said, I know the sample space, right? And then if you give me a sample space, I tell you that the probability of it must be 1. Okay. You tell me everything, I will say, this will give me number 1. Okay. So that is the quantifier of the future, right? You tell me everything, then one of them must be true. So we are not surprised by thing is something may not come, something come out that, but it's not in our consideration. So there's no surprise, right? As we said before, same random experiment, right? You know all the outcomes. So that seems to be 2 of them. I think is nothing deep there, right? Must be 0 to 1. You tell me everything, I will tell you that at least one of them will happen, so it must be 1, right? 2 of them are just SEP, there's no bite at all, okay? What is the important here is the last one, the last axiom, actually build up the whole enterprise of probability, the last one, okay? This guy is what we call the additivity, you will say, okay? Which the following. If you tell me that an A is bunch of outcomes, and these outcomes are mutually exclusive, the probability of this event is the probability of some of these outcomes. Okay, so it's simply a cake idea. I have a birthday cake. Okay, I want to measure how big the cake is. Okay, I can just measure it, or I can cut the cake into several pieces. When I cut the pieces, means that they are mutually exclusive, right? And I measure each cake size, add up together. Then no matter how I do it, I measure it in the big way, or I cut in small pieces, add up the measurement into each small pieces, they should be the same. It cannot be larger, cannot be smaller, okay? Right? Just like we can divide and conquer, right? I can divide the big thing into small parts, add up the small parts, that should be the same, right? Just like, what's the probability of an even event, rolling a die? It should be probability of adding up probability of 2, probability of 4, probability of 6, right? Or a probability even number must be equal to probability of 1, add up probability of 3, and probability of 5. It can't be larger or smaller. Okay? By probability, it must follow this concept. Okay? And surprisingly, this is the basis of probability. Okay? And you may think, okay, what are we doing? I mean, isn't it normal? No, it's not normal. Actually, it spent mathematicians more than 100 years to figure this out. Okay? And if this violate, it goes to another thing, but we are not interested in going into that as well. But there's a you can relax this thing, then it's not probability. It becomes something different. If you learn fuzzy logic, that will be you violate some of these things. You will measure something else. But probability must satisfy this idea. Adding up, okay, is equal to this. And those people who are math talented would say, is it normal, okay, to have this? Why we need an assumption? If you did M2, you do advanced math. In fact, I don't say n is finite or infinite. Okay, and the real bytes comes from n can be infinite. So that is where the faith needs to be there. You have infinite, you cut it to infinite small, it's still adding up. So that is the main bite of this theorem. But we don't want to emphasize on the math part. So, but that is the infinity thing is really the main thing that distinguishes the thing. Because why you care about infinity? Because when we talk about the data, when discrete data, there's no problem. You 1, 2, 3, 4, 5. But when it's continuous data, then you really need the infinity thing. And if you learn advanced math, infinity thing become crazy. So that is why mathematicians actually spend 100 years to give the foundation of probability. That is the infinity thing. But we're not math class. This is sufficient for our purpose. But do note that this is the infinity thing is the main thing. So let me see why this is, we can say probability without random experiment. We can make some assumption, then probability will be there. Okay, we can introduce knowledge to the system, and then we can define probability. Okay, that's why we can define typhoon thing. But let's see how we do it. So suppose I roll a die. Okay, and how can I have probability without rolling it? Okay, we make some assumption on the die, then we can do it. So assumption on the die is a fair die. Okay, we'll do it soon. So the first one is XM2. XM2 said the sample space must be 1. Okay, so with the first line, Probability of S is 1. Is that okay? The second bullet point said, okay, from the axiom 3, great. Remember the axiom 3 said what? Probability of sum, right? The whole will be equal to sum of its or part. So probability of the sample space is probability of all its component. The component is 1, 2, 3, 4, 5, 6, which are mutually exclusive. So it's adding up everything. Okay, fair? Now, here comes our assumption. There's a knowledge about a system where you are coming from the science, coming from the data, coming from engineering, coming from everything, right? So in this case, coming from engineering, you can be consistent with the random experiment idea. You can toast a coin 6 million times. You figure this out, okay? And you figure out this equally likely, and you think that the probability should be the same. Okay? If they're the same, you solve a system, right? 1 equal to 6 of the unknown. Each unknown will be 1 over 6. Right? So here comes the engineering part comes in. Right? The engineering part, the data part comes in, right? So you may ask, right? This is how the probability related to our class. Because the data or history or engineering knowledge tell us why they're saying. Of course, if the die is unfair, right? You are putting some tricks on the die. Maybe 1 is twice more likely than all the other number. You can also still solve it. Okay. And once you solve it, you can assign for every event, right? How event of even is just adding up 2, 3, and 4. So we can calculate every single event. So you can quantify your uncertainty based on data, based on knowledge, based on history, right? So that is the probability that without random experiment. It's based on assumption, based on what we think the world should be. Okay? Is that okay? So that is the 3 axioms actually turn out to be very powerful. Okay, we just need these 3 things. Okay, it's very trivial, but only thing is adding thing, right? Adding thing. Okay. Is that okay? The first time you saw it seems to be very trivial, but I will promise you that I will give you more to show you this powerful 3 axiom can do a lot of stuff. Okay, and actually derive everything we know from probability. Okay, is that okay? So as I said, the power of it comes from infinity. Okay, and that is the main part, I mean, to do it. But of course, we are not in the math class. You have to go to the math class to understand this. Okay, even the statistic, I think the stat department don't discuss this. You need to go to math department to understand the implication of this. Okay, it's I think it's a 4,000 class in math department. They study what we call the measure theory, and probably they will talk about this, the foundation of probability. But I don't think anyone would do it. Okay, so that's okay. You don't need to know it, but this is how it. Okay. As I said, right, the classical definition rely on experiment, but axiomatic can be just mathematical object. Right? So to illustrate the power of the new rule, we want to show you that these axioms actually lead to the rule that we know how to do all the calculations. And that's actually, you learn all this in the high school. Okay, the complement rule, okay, and also the order rules that we require. Okay, because all this rule at the end will lead us to a very famous important rule called the Bayes theorem, which we'll cover next week, hopefully. That will give us how we can learn. Okay, we talk about machine learning these days, right? And we will learn one rule is called the Bayes rule, which is part of the machine learning. Okay, and actually this is how machine learns. I mean, there's one way to machine learning. It's called the Bayes theorem, and of course there are other way machine learn, but this is the one of the way that is also the way that the most correct one. And the other way is more shortcut, but so now let's have the complement rule. The complement rule is rather simple. Okay, if AC is the complement, okay, then they're correct by this formula. Probably A is equal to 1 minus the complement. Okay, and we have seen that before, but this is actually followed directly from axiom 3 and axiom 2, because A and its complement is mutually exclusive. They must add up to the union, which is sample space, which is 1. So that's why you have this formula. Not going to do the proof because I don't see anyone who want to interested in proof, but the proof is there. If you know some math, is trivial. I rather want you to look at the example before we have a break. Okay. So how can you calculate the probability of less than 6? Okay. Of course, you can do the counting, right? Because outcome there's 6 of them. You can count 1, 2, 3, 4, 5. Right? Then you can calculate this particular case, right? So the complement of less than 6 is actually equal to 6, right? Because less than 6, the complement is actually 6. You take out the thing, but you know that the probability of 6 is a fair die, is 1/6, right? So that's why use complement rule is you subtract from 1/6 is 5/6. Okay, and you may ask, isn't it trivial? Okay, and it's not that trivial, because if you need to calculate the complement, which is 1 up to 5, you need to know how the probability assigned 1 up to 5, which require you to know the knowledge of those, right? If you don't have those knowledge, you only have knowledge of 6, okay, your data on 6, right? Complement will still tell you how you can derive those. Okay, so that is the idea, right? Because sometimes the event itself is very complicated. You don't know how to do it, okay? Or we don't have a expertise to assign for each single thing, but you know it's complement, which can be easily quantified from data, maybe, right? Then we're able to do that. Okay, so that is the main power of this, and you will see very soon. Okay, and this is the graph. Then we'll break. So the graph will be, I don't know what's inside, but I know what's outside. By taking out what's outside, what is left is inside. And you know whole thing is 1. You take out 1/6, then what is left is 5/6. Okay, so that would be the thing I want to say before the break. So I know that you're tired, so let's have a break of 15 minutes as usual. In the meantime, I welcome you to do the U-reply. So we will resume at 10:30 as usual. So feel free to fill that in. And it's still anonymous at the moment, but starting from the next week, because actual period is over, we will continue to U-reply, but we will do an anonymous version. I will not check your names explicitly. I will check it at the end of semester, right? Because or if you are not in the class, I was asked where you are, then I know, but I'm not actively checking. Okay. So have break. So let's resume at 10:30. If you're tired, get a coffee or tea, or do some exercise can make you stay awake. So let's get started. So we have 9/21 people fill in. So let's see what we have done. Oh, so let's make screen bigger. Question? So far, not yet. I'm hungry. I'm a bit hungry. Hi. What's that? I can't see, but what's there? Well, I can't see that one. Good morning, I guess. So the main question here is, what are the difference between regression and covariance? Okay, and both of them are finding way out the strength relation between. Yes. So we ask some people already reading the last set of slides, regression, which is last topic of our class. Asking what is that? Okay. And first thing, define covariance first. Recall covariance is just checking out if You have two variables, x and y. X and y above the mean at the same time and below the mean at the same time. Why? Because that's the formula. We have this. I'm just being lazy, want to write, so I just go to the slide there. Say if x above the mean and y above the mean, they multiply positively. They below the mean same time, then also positive, right? Because it's like this, right? This is positive, positive, and negative, negative, right? So it's basically positive means they are strongly related in positive sense. Negative means negative related in negative sense. And that's it. That's a measure. And as we said, the most useful one is correlation, right? Which you divide by standard deviation. By doing so, you would say everything would become -1 to 1. Okay? And by 1, which means a line there, not 1 is like this shape. 0 means you can't really have a line. It can be horizontal, can be upward sloping or downward sloping. Negative like downward sloping and negative one like this one. So that's correlation. Okay. And what's regression? Okay. And since you asked, I want to go formally, so let's go to the last set of slides, which is regression. So regression is a very deep topic, but what it does is simply I have a scatter plot. I want to find the best line to feed the data. Okay. So what is that? Is remember correlation, it just describe how the two variable is. Then no new knowledge generate. If I have a scatter plot here, I create a line there. So we have created new knowledge. Why? Because the data, say for example, doesn't have data of 28. When x is 28, y have nothing. There's nothing in the data. So by saying that x and y are related by a line like this, we generalize the knowledge from your data, which is finite number of data points, to infinite number of line there. So it's an extension, right? We are saying something that is actually not in data, extend knowledge to create a line there. Of course, still, you will still see later when you try to draw a best line, the slope of this line is closely related to the covariance or the correlation. We'll define it, but I don't want to jump too ahead the last class because otherwise we're done for the whole semester. But the formula I can show you, which will show you this how you have the best line is to minimize the vertical distance, square distance, and the formula is the slope is covariance over variance. Actually, it's related to what just asked. Okay, and remember when you write this, you are building a line there. Okay, and that's the first thing. That is, we generalize our knowledge from the data point to everything is not there yet. To the first thing. The second is regression in our class only cover x and y, right? But potentially, you can fit the line in a three-dimensional space. You can have x, z, and y. Okay, you can use two variables to explain the third one. Good. How do you what was that? But maybe you can think in this way, right? If you want to predict typhoon, right, you use, for example, the cloud and the wind speed, say two things, right? Or you want to predict your GPA, right? One is how much time you spend on the class, how much time you spend outside the class, right? Both of them will jointly determine your grade, right? If you just study at home, not come to class, that probably doesn't work, right? Both will be positively related to your final outcome, right? So in regression, although in our class focus on 1x, if you do the 2021, which is after this class, you study that actually you can determine by more than one dimension. or indeed you can do many dimensions of data that determine your outcome. Okay, so and then regression, you can see, is a building a model to explain things based on your data input. And actually that is LLM, right? You give him you give him a bunch of text, right? Based on the previous text, you predict the next one, right? That's large language model, right? The ChatGPT, right? You give then that's basically that predicting the next text, and that is one way to do it is full regression. Okay, and you can see basically the LLM is no different from a series of regression, but the regression is very complicated. It's a 1 billion trillions of regression along the way. And if you look at YouTube video, that's actually very similar to what I said. Okay. But indeed, I mean, LLM is even simpler than regression. But anyway, I'm not going into detail from that as well. But that will be something related to this one. I hope I answered your question. Just covariance is finding out in the data how they're related. But regression extend the knowledge from data to the things not in the data as well. And you build a model, mapping model, which is a line in our case, to extend what we know, right? Because things not in data, we still say they are related by the line. So the line is substantial generalized from the data, right? So that's very important. Although it looks trivial to draw a line, but the line actually say way more than you think. Okay, and in order to make it valid, we have to study the whole semester to why that line would make sense and how to use that line. That's the main thing about this course. It actually will come to the very end. And if you go to the next semester, you should study that, then basically telling you that how to do this line properly, generalized in multiple dimensions and various cases. And that's what econometrics is about, mostly. Okay. I hope I answered your question. Don't worry, this actually will be the main thing about our course. Okay. Everyone get it right? Today's Monday. Today is Friday. So thank God. It's windy? No, I think outside the wind is nothing, but it's okay. Probably. I think it's probability. Yeah, complete partition, free axiom, yes. Pop B, yes. Okay. I think you are good doing right. Okay. So the main thing I think is the free axioms, which is the modern definition of probability, which doesn't rely on random experiment. It can now the free axiom would allow us to define probability using data, using historical knowledge, using engineering perspective, without really doing the experiment. So that's why it's really flexible. Someone say something in the Zoom. No, nothing. So let me forget about this thing. So that the next thing that we want to say, can I do full screen? No. Why it's not? Why I'm not allowed to do full screen? Yes. So the next thing to say is the other rule is what we call the addition rule. Okay. So axiom 3 said the union is equal to sum of its part if they are mutually exclusive, right? It's like cut the cake in 2 parts, then probability of the whole is equal to sum of its parts. But what happened? The parts are overlap, which means that they are not mutually exclusive. How can we do, right? Because we don't have luxury of every time we have that happen. So turn out that it's not something too terrible. The probability union is the sum of its part minus intercept, which means that you're adding up its part minus the overlapping. This seems to be very crazy looking formula to those who worry about math. But I assure you, this is what you learn in kindergarten. Okay? How? Look at the graph picture. The A is the red circle, probably A. B is the purple circle. Okay? And A intercept B is this number X shape or infinity shape. Okay? Area of the infinity shape will be equal to the circle, red circle A, plus the blue circle B minus the duplicated region, which is the plane. Let me say it again. In case you don't know, let me actually draw a picture, because that will help you to remember. So I want to calculate this. Right? And first, the red one is A, right? So A is this one. A. And this blue one is B. A plus B. Okay? But do note that there's an overlapping region. You double count it, which is the purple one. So this purple is here, the purple is here. Okay? You subtract this A intercept, right? Because this is what this overlapping region, because you count it twice, right? Then will be equal to exactly this A union B. Okay, I hope that's clear. Of course, if you want to prove it, you need more elaborate math, but graphical representation, I think, is very clear. Right? It's a kindergarten thing, right? You have the duplicated region, you take it out, right? If you double count it. Okay. At least I think, if not in the kindergarten, it's already in primary school, right? You calculate two regions and overlap, you take it out. Okay. Now with this knowledge, we can go back to our slide. That's definition. And let's apply it to our scenario of rolling a die. So you have a question: what is the probability that you have even number or greater than 3? Okay. And how we do that? You would do it, easiest way is to look at actually what this happened, right? What's even number? 2, 4, and 6. Greater than 3 would be 4, 5, and 6. Okay. Or means that either of them happen, is the union of them, because or is union. So we can do it by list them out. Is 4, 2, 4, 5, and 6. Right? And it's a equally likely each one, so it's 4 over 6 or 2 over 3. So this is the direct calculation, right? The very last bullet point, right? But want to illustrate this is by doing divide and conquer. You divide part by part. Okay. We know the even number is equally half likely, and greater than 3 is also equally likely, 3 over 6. Okay. And we want to know the intercept. What is the event that they are jointly true, which is 4 and 6? Okay. Even greater is even number greater than 3. So only 2 numbers out is 2 over 6. So you add these 2 up minus the overlapping region, you get 2 over 3. Okay. You can do it this way or do the other way around, right? So the direct method is easy because AM, you can easily do the union. But sometimes this is super complicated to calculate. But the first method in the direct method actually is easier. So that's why we need this rule. Okay. So this diagram, right? So 4, 5, 6, 2, 4, 5, and 6 is this plus this minus this, right? So now we give you the table, the two-way condensed table. We promise to show you from the first class. We come back, right? The same table, we have this in the first class. So if I have this table, remember what does that mean? This means that 15 male pass exam. Now I randomly pick up a person from this class. Okay. And what is percentage of male? Will be 40 over 80, right? How many, what probably the students pass? Will be 35 over 80. Okay. What is men and pass? Will be 15 over 80. Okay. But now the question is, was male or pass? Okay. Male or pass. Okay. One way to do it is to say male or pass means look at all. This is this diagonal upper triangle here, right? 15, 20, and 25, right? This is the male of 15, 25, and the female will pass as 20. So we just add up the 60, so 60 over 80. But the other way around to illustrate this is to use the idea of the addition rule. You take the male and the pass minus male and pass. So you take this answer plus this minus this is directly for this. So this illustrates this. But of course, I make the example so simple. So it seems to be direct method is still easier. But later you will see this in fact many times are easier. Okay. But bear with me. Okay. I hope this is clear. The next little bit tricky and looks trivial, but this is turned out to be very important rule. We often use it. Okay, not by itself, but together with the rule we will see later today or next week. Okay, it's called the total probability rule, which is not something too difficult to see. If the probability A can be decomposed in two parts, which is A intercept B and A intercept B complement. Okay. And that is A with B and A without B. Okay. So why is important for this one? Okay. But that simply means the graphic means if A is here, you can have two parts. This part is A without B. This is A with B. Okay. And this can be also generalized in this way. If A up to N partition, probability B is sum of each element intersect B and add together. So what does that mean? It looks like complicated. But you will see that when we talk about Bayes rule. Okay. With the end of the chapter, we will see this again. Okay. Don't worry. Just be patient a little bit. We'll use this rule very often to do the calculation. Okay. Now let's make application right now. Because now gamble become more common, right? And then when you go to gamble, they don't show probability, but there is so odd ratio, right? Because and it will tell you that the odd ratio can tell us what people think about probability. Okay, but let me quickly define it. Okay, and as I said, odd ratio is indeed people think about how things going to happen or for event that before we have probability. Actually, this is what people measure the thing before probability exists. So odd ratio in favor of A, you can forget about this, but this is what it means is probability over its complement, okay, which PA over 1 minus PA, okay? So you can see the odd ratio, if PA go to 1, this thing go to infinity, okay? And if PA is 0, this is 0, okay? So instead of 0 to 1, the classical way of thinking things, how likely they are, is 0 to infinity, okay? If odd ratio is 1, then actually it's equally likely, okay? So that is what is 1 is means half, right? So this is how people think about how to describe that in the history, okay? So you may ask, what is this? What is odd ratio? Okay, odd ratio, as I said, is just another way to describe how likely event is. Okay, and as I said, 1/2 probability means also always a 1. Okay, and I hope you agree that probability is easier to understand than odd ratio, right? Because odd ratio go to infinity, right? And odd ratio of 1 million, what does that mean? Odd ratio of 1 trillion is what difficult to say, right? But this is a better way to describe uncertainty. But you may ask, okay, what's the use of odd ratio? Okay, and given now with probability, why we need to learn some old thing, right? Is it going to be related to history, right? Not about history. It is because there are betting market, okay, and betting market usually stay in odd ratio, the betting odd, and the odds actually reflecting probability, and that's why a lot of people using the betting market to infer how people think about things going to happen likely. Okay, what about this? Let me talk about this. So if you go to bet, okay, you bet money, they will tell you, okay, odds are 4-1, okay, which means that if you put up $1, you win, you get $4. You lose $1, right? So that is very easy. Okay, so that is the definition. It's the odd ratio, but not always just odd, betting odds. Okay? But that is closely related to odd ratio, which I'll elaborate. So if the casino is very competitive, okay, which is true because online there are many betting things, right? And actually the odds will be representing that how casino thinks things would happen. Okay, but casino adjusts odds according to people think. So what the casino odds actually reflecting what actually the public thinks, because you can bet both ways, right? You can suppose the odds of team A versus team B, right? And the other team B versus team A, right? And you can buy whatever, right? So the odds actually reflecting in general public how people think about the odds. Okay, and let me show you the example. Okay, and because casino is very competitive, so the odds will be reflecting a fair bet, which means that if the casino should be breaking even about the odds. Okay, what does that mean? Let me show you the example. So if you roll a die once, okay, what is the odd in favor of number 6? Okay, remember odd ratio is just probability of itself over its complement. Okay, probability of 6, if it's fair, we don't know it's fair, but suppose it's fair, then it's 1 over 6. And then this 1 minus 1 over 6, right? So this is 1/6, and the denominator is 5 over 6. So you cancel out the denominator. 6 is 1 over 5. So the odd ratio is 1/5. Okay. So in the casino, if the casino is fair or there are many casinos they're competing, so you should see that the odds should be 5-1. Okay. Why? Because 5 out of 6 times you will lose $1. 1 out of 6 times you have to win $5 to even out the loss. Right? For example, you have 6 million, you pay 6 million times. Right? 1 million times you will win, 5 million times you will lose. Right? So if you win, you lose $1. So you lose $5 million. And you win 1 million times, you have to win $5 for each round. So it must be 5-1. Okay? So you can imagine you reverse this idea. If the odds are 1-5, it does imply that the dice are fair. You can infer the probability, right? Because this x, this is 1-5, then you can calculate what x is. Okay? And what does that mean? It means that suppose now we are going to have a gamble on basketball, right? The horse racing society tells the odd. And then you do this, given the odd, you reverse it and solve for this number, then can tell you the probability of winning. Let me give an example because I think many of you will still be puzzled. Suppose we have the following. Okay? Suppose now we have a team A versus team B in basketball. Okay? And horse racing association tell us the odd of winning, the odd if you bet A, right? The odd ratio is what? Say suppose 4-1. Okay? Suppose A means that you bet $1. If the team A wins, you win $4. If the team A lose, you lose $1. Okay? Now suppose the horse racing bet is competitive, which means that you should have 1/4, this x, 1 minus x. Okay? X will be the probability that team A wins. Okay? You can solve this out, which I hope you know how to solve. This is high school math. You cross multiply, which is 4x equal to 1 minus x, right? That means x is 1/5, right? So in that case, the horse racing society or the betting company is saying that team A is going to win 25%, team B is 75%. So by using the betting from this company, you can predict what's probability there. Okay? And you may ask, is it something crazy doing here? No. Actually, in financial market, you do that. The options, option, they have pricing. And actually, based on option pricing, you can infer back the risk of the stock, right? That's called the implied volatility. If you suppose you learn option pricing in 4000 class in finance, using the market to infer what people think is something common. Okay, you can actually go back from the odd ratio, the odds from the casino, you can know how likely team A is going to win. Okay, and this is not uncommon because you have online casino betting almost everything, right? Even for the weather forecast, right? Because you can go to Chicago option market, they trade a lot of weather contract, And based on that, actually, you can look at how people think about the future weather, right? So all these things can be bad because it's there. So that is the application. I hope that allow you to see what's going on there. Okay? Is that clear what we're doing? Yes, a question? You win $4. You bet $1 for team A. If the team A actually win, you win $4. You lose $1 bet. Yeah, the solving. Yeah, yeah. Yes. Yes, that is what the casino think that how likely team A wins. Okay. Of course, that means that because either A or B win, then B is 75%. Okay. And that is the application. So you can go to the casino, right, and see how each horse might win, right? Winning horses, you can calculate that probability, and then you can do all the calculation, and you can see, right? Even though you can't have probability which team will win, but by looking at the casino thing, then you know actually how, on average, the market, how people think about stuff. All right, and that actually is very useful because you can look at the market. You're not expert, you can't assign, but you can look at how people, where money goes, and you can guess what's going on there. Okay. Is that okay? So I think we give you one application, which I think is very good. It's very useful. When you do finance or you do what other thing is very, very nice stuff. So the next is talk about, I think there's one of the most challenging part is about the conditional probability. You might or you may not study that in your high school. If you do M1, then you have that. But if you do M2, you haven't seen it. Okay. So that is something that related to learning as well, is how can I update our probability if I know something had happened? Okay. So what this example would do is the following. Okay. I guess the example we usually set is like this. Let me give example. Okay. I used to give this example in this way. So I guess in old days, right, that terrorists running around, right? Still the Bin Laden is still there. I don't know whether you know Bin Laden. It's an old terrorist. But imagine there's a area. So suppose this is a allocation. Okay. It's the map. Okay. It's the sample space. Okay. And you know a terrorist or a plane, whatever, want to hit a target. Your enemy is here. You know, figure out that the intelligence tell you that your enemy, call it enemy A, I guess enemy A, right? Enemy A is running around, okay? It's a target, okay? It's running around, okay? Or people these days talk about China is going to strike an aircraft carrier, right, of US, right? So you can imagine the US aircraft carriers around this region, right? Because you see the satellite from the sky, then can be moving any place in this region, right? And these days people said, okay, the Chinese army can fire a nuclear missile to hit, right? And the question would be, suppose there's a World War III happen, okay? Chinese nuclear weapon actually hit this region, bomb, B, okay? And because the nuclear weapon, everything in B evaporate, right? So the question is, how likely, you know, the nuclear weapon explode this region, and assume the nuclear weapon destroy everything. Then the question is, how likely that the aircraft carrier has been destroyed? This is a question, right? The military question, right? So consider that B has killed everything here. Okay, how likely that actually you hit the target? Okay, that's the question. So go back to the example like this, right? Knowing that this been explode, how likely that A has happened? Knowing B has happened. Okay. So the formula turned out to be not difficult. A and B is happen together. B is true. So only A has happened, right? A and B, no B is true. So only B is relevant. Okay. So that's why you only care about A intercept B. Okay. And because probability must be between 0 to 1, you divide it by B to normalize it. Okay. So it looks a little bit tricky. Okay. But let me show example. So suppose I wrote it down 1, 2, 3, 4, 5, 6. Even is 2, 4, 6, and large is 4, 5, 6. Okay. And even and large is 4 and 6. Okay. Now the question is the following. If I know, I tell you it's large, L happened. The question is how likely that E has happened, right? I use large. How likely that is even? Okay. Then one way to do it is to say, okay, large is true. So the only relevant sample space is actually 4, 5, and 6, right? Because 1, 3, 5 is not there. Okay. Then it's very simple. You look at this, 4, 5, and 6. Okay. And E just 2, 4, and 6 because this is no longer 2 is no longer relevant. Only even number is this. So the probability that even number given large is just 2 out of 3 outcomes. So it's 2 over 3. Okay. And this is the way to do it, but in more direct way, you can just use this formula. Just by definition, probability E given L is just E and L over L. Okay. With just 2 over 6 over 3 over 6 is 2 over 3. Okay. And this formula you can prove, but usually for the undergrad, it's just definition. We don't prove it. So this is coming from define it. Okay. Just definition. Okay. What it means is like this. The Venn diagram here. Okay. 1 and 2 is outside. Even number is here. Large number is here. Now we know that large number occur. So the sample space strength 1 and 3 is not relevant anymore. 2 is not relevant there anymore. So even number is just only 2, 4, and 6. And over only the sample space is only 3. Okay. And this is the formula, right? We know something happened, how we can update it. Okay. So that is the idea. Okay, so the example like this, we have probability A and B, and A intercept B is 3. What's probability that A given B, okay, is use the intercept over what you condition it on. Okay, so it's 0.3 over 0.5 is 0.6. Okay, so that is definition. You can check it again as well. Okay. So I want to talk about this last rule, then we are done. So this last rule is what we call the multiplication rule. This rule is nothing new, but you just multiply the denominator to the other side. Multiply B on the other side. Okay, there's nothing new there. Just You can see, right? Divide B, go to this side. Okay. What is funny is because A and B can be swappable, right? So A and B just swap this way. Okay. So, and you look, this rule looks innocuous, nothing very deep here. But if you ever actually calculate anything probability in the future, this rule will be something that you use very often. Okay. And we'll see the application immediately. Okay. So this last example I want to talk about. Okay. So this is statistic people will like, drawing balls from an urn. Okay. So the question is, I have an urn with 3 blacks and 3 white balls. Okay. I draw 2 balls from there. And without replacement means I draw 1 ball, don't put it back, I draw again. Okay. The question is, what's probability both balls are black? Okay. And of course, you can actually, how do you solve this problem? Of course, you can list out all the possibility, right? The first one is black, the second one is black, the first, because we have 6 balls, right? Then you can list out all the possibility, right? Which will be 30 outcomes, right? Can be first ball, second ball, first ball, third ball, first balls, there are many cases, all right? And each outcome is equally likely. You can do that, right? Because what I said is because there are 6 balls, right? So we have you name the ball 1, 2, 3, 4, 5, 6, right? And there will be 1, 2, 3, 4, 5, 6 here. There will be 36 outcome, but once you draw the ball, you can draw it again. You take away this 6, then we have 30 balls, 30 outcomes, right? Each outcome equal likely. You can count how many balls are bad, and so on and so forth. But this is very tedious. Okay, can we do something easier? So to do it easily, we can do the following. We define the event first ball is black by B1, and second ball is black by B2. Okay, the question is asking is what is both are black, so the B1 intersect B2. Okay, when you draw the first ball, there are 3 whites and 3 black. Okay, so you are closing the eye and draw. So out of 6 balls, 3 are black. So half of them is likely to get a black ball, the first ball. Okay. What about the probability that second ball is black? It's hard to do, but we know one thing is, if the first ball is black, what's left there, it will be 2 black and 3 white. Okay. All of the 5 balls left, 2 of them is black. So that's why it's 2/5, right? Because the 5 balls, 3 whites and 2 black. So we know this is easy to see, right? It's not easy to see what's probability of B2, but it's easy to see probability B2 given B1 happen, right? So using what we call the multiplication principle, we can multiply B1 and B2 given B1, right? Because that's the definition of the multiplication rule, right? Is intercept is A given B times B or B given A times A, right? So in that case, you can multiply 2/5 by 1/5, you get 1/5. Okay, so that is how we get the solution. Okay, and in the next class, we want to show you a tree diagram, which is the most useful thing to graphically illustrate the idea. And this tree diagram will be the most useful when we talk about Bayes' theorem. So this, you have to understand this very nicely, then we will understand the whole chapter very easily. So I will see you next week. Have a nice weekend. And just to remind you one last thing is the Blackboard has a self-checking quiz. So you can do it at your free time, because many of you ask me, do you have more exercise to do for fun? Yes, you do. And this quiz is as long as you do, you get the credit for the participation marks. So I don't care about whether you get it correct or wrong. Once you do it, then you're done. Yeah, part of that, yeah.
But get it wrong.
Same. Just once you do it, then you're done. Yeah. Not for all, but I mean part of the assessments, part, yeah. Part of the content code. Attendance has